So why am I so excited to talk about reduced row echelon form matrices? Well, studying reduced row echelon form matrices is pretty interesting. There are certain adjectives we can use to describe reduced row echelon form matrices that end up proving useful. So now I want to talk about what's called rank and nullity. These are two of the most important concepts in all of linear algebra. So let's say that we're working with a matrix that's in reduced row echelon form. The first thing, so to remind yourself, right, this is in reduced row echelon form. There is a row of zeros, but it's at the bottom. We have 3 pivots. They move down and to the right, and they're the only non-zero entries in their respective columns. So I have my pivots. The first thing to learn is that every reduced row echelon form matrix has pivot columns and non-pivot columns. So when we're talking about the columns of a reduced row echelon form matrix, we'll call the columns that have pivots in them pivot columns, and we'll call the columns without pivots in them non-pivot columns. So in this matrix, we have 3 pivot columns because we have 3 pivots in this reduced row echelon form matrix. There are 2 remaining columns, so there are 2 columns that don't have pivots in them. These are called non-pivot columns. So once you have your matrix in reduced row echelon form, it's quite simple to figure out which are the pivot columns and which are the non-pivot columns. Simply locate your pivots. The columns with the pivots in them are the pivot columns. The columns without pivots in them are the non-pivot columns. All right, so now one of my favorite definitions, rank. So if we're working with a matrix in reduced row echelon form, we call the rank the number of pivot columns. So the rank is the number of pivot columns, which is really just the same thing as the number of pivots. So if we go to our example here, remember rank is the number of pivot columns. All we need to do to figure out the rank is just count the number of pivots, and that tells us what the rank is. There's 3 pivots here, which means there's 3 pivot columns. That tells us the rank is equal to 3. Now, rank couples nicely with this other concept called the nullity. The nullity of a matrix is the number of non-pivot columns. So here, we're working with a 4 by 5 matrix, and the rank is 3 because we had 3 pivots. Well, the nullity is the number of non-pivot columns. Well, since there are 3 pivot columns, there's 2 other columns remaining. So that means that there are 2 non-pivot columns, which means that the nullity of this matrix is equal to 2. So we have pivot columns and non-pivot columns. The number of pivot columns is called the rank, and the number of non-pivot columns is called the nullity. These 2 concepts are extremely important. Okay, so here is a much larger matrix. This matrix is in reduced row echelon form, and I went ahead and I found all the pivots. In this case, we have 4 pivots. Because there are 4 pivots, there are consequently 4 pivot columns, which means that the rank of this reduced row echelon form matrix is equal to 4. What about the nullity? Well, to calculate the nullity, we just need to figure out the number of non-pivot columns. So how many columns in this matrix don't have a pivot in them? Well, let's just count them. We have 1, 2, 3, 4, 5, 6. So in this matrix, there are 6 columns that don't have a pivot in them. So the nullity of this matrix is equal to 6. So here we're in reduced row echelon form, which means it's easy to locate where the pivots are. Here we happen to have 4 of them, so there are 4 pivot columns, which means the rank is 4. And when we counted the number of non-pivot columns, we counted 6 of them, so the nullity of this matrix is equal to 6. Again, if you're in reduced row echelon form, it's very simple to figure out the rank and the nullity. Figure out the number of pivot columns, that's the rank. Figure out the number of non-pivot columns, that's the nullity. And now we arrive at, believe it or not, one of the most elegant theorems in all of mathematics. At least this is one of my favorite theorems in all of mathematics. This is called the rank nullity theorem. And the cool thing about this theorem is that there are certain ways to state it where it seems like a completely obvious thing, but then it creeps up in other areas where it's far less obvious. Hopefully we've set things up here so that the statement of the theorem is relatively easy to understand. If you think about it, a matrix that's in reduced row echelon form has only two kinds of columns. There's pivot columns, which is the columns that have pivots in them, and there's non-pivot columns, which are the columns that don't have pivots in them. Well, every column fits one of those two descriptions, so when we sum the number of pivot columns with the number of non-pivot columns, we get the total number of columns. This is the idea behind the rank nullity theorem. So let's state this more rigorously. Let's say that R is m by n, and let's say that we're working with R, which is in reduced row echelon form. So R is a matrix with m rows and n columns, and R is in reduced row echelon form. The rank nullity theorem is one simple equation. It says that the rank of our reduced row echelon form matrix plus the nullity of our reduced row echelon form matrix is equal to n, and an even simpler way of thinking of that is simply the rank plus the nullity is always the number of columns. So let's see this in practice. Again, the rank nullity theorem says that the rank plus the nullity always equals the number of columns. And one of the useful things about an equation is, especially an equation like this, is that if you know everything except one piece of information in the equation, you can use the equation to infer your missing piece of information. In other words, the rank nullity theorem is a relationship between three numbers: the rank, the nullity, and the number of columns. So if you know one, or if you know two of the three numbers here, you can use the rank nullity theorem to infer the third missing number. Let's see some examples. So here, I'm giving you an example where I'm pretentiously writing R is an arrow, or can be viewed as a transformation from R5 to R9. Remember, this is really just a pretentious way of saying that R is a 9 by 5 matrix. And let's say that someone told us that the rank of this matrix was 2. Well, if the rank was 2, and we know that the rank plus the nullity equals the number of columns, it must be the case that the nullity can be solved for here, and it should be the number of columns minus the rank. So in this case, the number of columns is 5. Someone has told us the rank is 2. 5 minus 2 is 3. Now we know the nullity. So here we had an example where we knew the shape of the matrix. We knew that the matrix was 9 by 5. Someone told us that the rank was 2. And then we used the rank nullity theorem to figure out ourselves that the nullity had to be 3. Let's see another example. In this example, we're representing R as a process that takes vectors in R12 to vectors in R7. Remember, this is just a fancy way of saying that this matrix is 7 by 12. So there are 7 rows and 12 columns. Let's say that we don't know the rank, but someone tells us that the nullity is 4. Well, I know the number of columns, and I know the nullity, so I can use the rank nullity theorem to infer the rank. The rank should be equal to the number of columns minus the nullity. Well, the number of columns here is 12, and 12 minus the nullity would be 12 minus 4, which is equal to 8. So in other words, if you tell me that R is a 7 by 12 matrix with nullity 4, the rank nullity theorem automatically tells me that the rank had to equal 8. Great. Let's see one more example. Here, we're representing R as a process that goes from R to the question mark, so we don't know that number, to R6. And someone is telling us that the rank of this matrix is 5, and the nullity of this matrix is 3. So the question now is, well, R was a process that went from where to where? Or in other words, R is a 6 by question mark matrix. What is question mark? Well, question mark should be the number of columns, and the number of columns is always the rank plus the nullity. Since the rank is 5 and the nullity is 3, I automatically know that the number of columns has to equal 8, which is 5 plus 3, and that's the power of the rank nullity theorem. So this is a nice, I sort of like these examples because they're sort of nice examples of situations where you might have incomplete information, but the rank nullity theorem in these particular situations allows you to get full information.